In today's lesson, we are going to be solving trigonometric equations, and students will be able to solve those equations by using double angle identities, power reducing identities, and half angle identities. Thinking back to that activator, we had, for example, sine of 22 and a half. Well, that's half of 45, right? We haven't learned how to do a half angle, how to find the sine of a half angle, but that's what our objective is saying, that we're going to be using these half angle identities, power reducing identities, double angle identities. So that's what we'll be working with. Our activator, we looked at those determining trig values of uncommon angles, and our instructional focus is going to go through and we'll learn about double angle identities, power reducing identities, half angle identities, and then how we can solve those equations using those identities. So let's start out with double angle identities. For sine of 2 times u, all right, so if we have, for example, sine of just 2 times some angle that we know, it's the same as 2 sine u times the cosine of u. For cosine of 2u, there's a few different ways we can get there. It's cosine squared minus sine squared, or 2 cosine squared minus 1. Notice those two, and the last one for that matter, all three of these are just variations on the identity sine squared plus cosine squared equals 1. But cosine squared u minus sine squared u, 2 cosine squared u minus 1, or 1 minus 2 sine squared u. Tangent of 2u is equal to 2 times tangent u divided by 1 minus tan squared u. So here are some new identities that are going to help us along the way. Now, you might say, well, okay, that's great. You showed me some formulas, but where did they come from? Why am I supposed to believe that sine of 2u is the same as 2 sine u cosine u? Well, sine of 2u, the way I would look at this, sine of 2u, isn't that just the same thing as saying the sine of u plus u? And if that's the case, couldn't we then use what we already know about adding angles to come up with that identity? So let's see how that works. So sine of 2u is equal to sine of u plus u, which is sine of u cosine of u plus cos u sine u. Well, these are just the same, right? We're multiplying the same values because the angles are both u. We can change them both to say sine cosine. Therefore, when we add them together, we get 2 sine u cosine u. All right, so that is a double angle identity, and it's taken straight from what we learned about the sum identity. There are other identities like power reducing. So if I have sine squared or cosine squared or tangent squared, we can reduce that power. Okay, we can convert that to 1 minus cosine 2u divided by 2 for sine, 1 plus cosine 2u divided by 2 for cosine. And then it's just, you divide them to get tan squared, right? So we'd end up with 1 minus cosine 2u divided by 1 plus cosine 2u. And so once again, well, how do we go about proving this identity? All right, so if we start with this, cosine to the fourth minus sine to the fourth, and we want to prove that that equals cosine 2 theta. All right, cosine minus sine, cosine to the fourth minus sine to the fourth. Let's see how we would go about doing this. And the way in which we would do this is we can actually take it and break it down using the different identities that we know. Well, we'd start out though, cosine to the fourth minus sine to the fourth, that's just a difference of 2 squares, right? It's cosine squared plus sine squared times cosine squared minus sine squared. So we start out just with difference of 2 squares to get to here. Now, cosine squared plus sine squared, well, that's just 1. So it's 1 times cosine squared minus sine squared. Well, the double angle identity for cosine is cosine squared minus sine squared. So that's how we get from the start, cosine to the fourth minus sine to the fourth, all the way down to cosine of 2 theta. We are also able to determine some half angle identities. The sine of u divided by 2 is equal to plus or minus 1 minus cos u divided by 2. Cosine of u over 2 is equal to plus or minus 1 plus cosine u over 2. And for tangent u over 2, we have 3 different formulas that are all valid. Now, the interesting thing here, you might ask, well, where do they come from? We could go back and do a little exploration to learn about this, but where it really comes from, sorry about that, is this piece right here. Sine squared u is equal to all of this. Now, if I wanted to just take a square root, right, I could take the square root of both sides. I'd end up with sine of u is equal to the square root of 1 minus cosine 2u over 2. Now, notice cosine 2u. So this tells me the half angle of this. So if I changed u and kind of wrote it as, say, 2u is x, so if I say 2u equals x, that means u equals x over 2. So the sine of x over 2 is equal to 1 minus cosine x over 2, the square root. All right, so that's where that really comes from. All right, that's where that's being taken from. And the same is true for cosine and tangent, etc. So how might we use a double angle identity? If I were asked to solve algebraically in the interval between 0 and 2 pi, sine of 2x is equal to cosine of x. All right, how would I figure that out? How would I find where that occurs? Well, sine 2x I could rewrite as 2 sine x cosine x. And I want to know, where does that equal cosine x? So I could subtract cosine from both sides. I get 2 sine x cosine x minus cosine x equals 0. I can now factor cosine x out. Cosine x times 2 sine x minus 1 equals 0. So it's when cosine x equals 0, or and the other interesting one is this, 2 sine x minus 1 equals 0, or sine x equals 1/2. So where does that occur? Well, cosine x equals 0. That is going to occur at pi over 2, and once again at 3 pi over 2. And then when does sine x equal 1/2? That's going to happen at pi over 6 and 5 pi over 6. So those would be my that would be my solution set for this particular double identity. If we take a look at the book solution, that's exactly what they come up with, that same exact list. And they also mention that we can support this graphically by verifying that those are the intercepts of the function sine 2x minus cosine x between 0 and 2 pi. So you can always check by putting that in a graph and finding where does it cross the axis. We can also use half angle identities to solve problems. So for example, with sine squared x is equal to 2 times sine squared of x over 2, here we have that half angle, so we can use the half angle identity. So we could rewrite this as sine squared x equals 2 times, and this is the square root of 1 minus cosine x divided by 2. But then it's that whole quantity squared because it's sine squared, and so the square root and the squared will cancel out. So we end up with sine squared x equals, and then the 2 and the 2 will cancel. It's just going to equal 1 minus cosine x. We can rewrite sine squared as sine squared is the same as 1 minus cosine squared. So we have 1 minus cosine squared x equals 1 minus cosine x. If I subtract 1 from both sides, that'll cancel. I can divide by -1, the negative signs cancel, and I'm left with, when does cosine squared x equal cosine x? And the way we solve this algebraically is we're going to subtract cosine x from both sides. So we end up with cosine squared minus cosine equals 0. We can now factor out a cosine. So we have cosine x times 1, or cosine x minus 1 equals 0. So we know that this will be a solution when cosine x equals 0 or excuse me, or when cosine x equals positive 1. If we think about our graph of cosine, looks something like this. It's 1, it's 0, it's 0, and it would be back up to 1 way over here, but between, if we're looking at just the interval between 0 and 2 pi, we're going to have 1, 2, 3 solutions because we don't count 2 pi. So there should be exactly 3 solutions, and they would occur at 0, pi over 2, and 3 pi over 2. And we can find that, if we look at the actual graph of this particular function, sine squared x minus 2 sine squared of x over 2, we would have, where we have our x-intercepts, those are our solutions, that's 1, 2, we should have 3 solutions in that interval. And since we're going from, in this window, we're going from negative 2 pi to 2 pi, so 0, pi over 2, 3 pi over 2, that looks like our solutions would be correct. And the text actually goes through and confirms pi over 2 or 3 pi over 2 or 0 would be our exact values. So in this lesson, we explored the multiple angle identities, including double angle, half angle, and power reducing varieties. We used these identities in various situations, and we simplified expressions and solved otherwise difficult trigonometric equations. So you should be able to do those things. You should be able to use those identities to prove multiple angle identities. You should then be able to use the multiple angle identities to simplify or solve trigonometric equations.